Tonight, we're going to stare into the deepest mystery in all of science. What came before the Big Bang, before time, before space, and before anything existed at all? The answer should be simple, just nothing, empty void, pure absence of everything. But physics doesn't allow for simple answers, and the deeper we look into that moment, the stranger it becomes. Our mathematics stops working, our theories collapse, and we find ourselves staring at a boundary that might be impossible to cross. And by the end of tonight, you're going to understand why this isn't just an unanswered question, but a question that might destroy itself the moment you try to ask it, and why the greatest mystery in the universe isn't what came before the Big Bang, but whether before even existed at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what we know for certain. The universe had a beginning, not a beginning in the sense of appearing in some pre-existing empty space, but a beginning of space itself, a beginning of time, a beginning of everything. Around 13,800,000,000 years ago, the universe as we know it came into existence. Every galaxy, every star, every planet, every atom, every photon of light, all of it traces back to that moment. We call it the Big Bang, though that name is somewhat misleading. It wasn't an explosion in space, it was an explosion of space. Space itself began expanding, carrying matter and energy along with it. The evidence for this is overwhelming. First, galaxies are moving away from us in all directions. The farther away a galaxy is, the faster it's receding. This relationship was discovered by Edwin Hubble in 1929, and it's one of the foundational observations of modern cosmology. If galaxies are moving apart now, they must have been closer together in the past. Run the clock backward, and eventually, everything converges to a single point. Second, we can see the afterglow of the Big Bang itself. In 1964, Arno Penzias and Robert Wilson discovered something extraordinary. They were working at Bell Labs in New Jersey, using a large horn antenna originally built for satellite communications. They kept detecting a persistent background noise that wouldn't go away. No matter where they pointed the antenna, no matter what time of day or night, the noise was always there. At first, they thought it was interference from New York City, but the signal came equally from all directions. They thought it might be heat from the ground or the atmosphere, but the spectrum was wrong. They even thought it might be from bird droppings in the antenna. They actually cleaned out what they politely called white dielectric material. But the signal persisted. What they had discovered was the cosmic microwave background radiation, light left over from when the universe was only about 380,000 years old. Before that time, the universe was so hot that atoms couldn't form. The temperature exceeded 3,000 degrees Kelvin, which is about 5,000 degrees Fahrenheit. At that temperature, electrons couldn't stay bound to atomic nuclei. Everything existed as a hot plasma of free electrons and protons. In this state, light couldn't travel far. Photons would constantly scatter off the free electrons, bouncing around like balls in a pinball machine. The universe was opaque, like being inside a thick fog. But as the universe expanded, it cooled. Eventually, the temperature dropped below 3,000 Kelvin. Suddenly, electrons and protons could combine to form neutral hydrogen atoms. This happened rather suddenly across the entire universe in a transition called recombination. When recombination occurred, light could suddenly travel freely. The universe became transparent. Those photons that were released have been traveling through space ever since. They've been stretched by the expansion of the universe from visible light wavelengths down to microwave wavelengths. Today, we detect this radiation as a nearly uniform glow with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. The third piece of evidence comes from the abundances of light elements. In the first few minutes after the Big Bang, nuclear fusion occurred throughout the universe. Protons and neutrons combined to form the nuclei of light elements, mostly hydrogen and helium, with trace amounts of lithium. When we measure the ratios of these elements in the universe today, they match the predictions from Big Bang nucleosynthesis with extraordinary precision. The hydrogen to helium ratio, the small amount of deuterium, the tiny trace of lithium, all of it matches what we'd expect if the universe started in an incredibly hot, dense state and then expanded and cooled. These three independent lines of evidence all point to the same conclusion. The universe had a beginning. Space and time came into existence about 13,800 million years ago. Everything we can observe, every particle, every photon, every cubic centimeter of space, all of it emerged from that initial state. But here's where things get strange. What does it mean to say the universe had a beginning? What existed before that beginning? Your intuition probably tells you that if something begins, there must have been a time before it began, a moment when it didn't exist yet. But physicists tell us this intuition is wrong. Time itself began with the Big Bang. There was no before, no prior moment, no earlier time. The concept of before doesn't apply. This is deeply counterintuitive. How can time itself have a beginning? To understand this, we need to understand what time actually is, according to Einstein's theory of relativity. In everyday life, we think of time as something absolute and universal. We imagine it flowing like a river, carrying everything along at the same rate. We assume that when something happens here, there's a definite answer to the question of what's happening simultaneously somewhere else in the universe. But Einstein showed this picture is wrong. Time isn't absolute, it's relative. It's part of a four-dimensional structure called space-time. Space and time aren't separate entities. They're woven together into a single fabric. And this fabric can bend, stretch, and curve. In 1915, Einstein published his theory of general relativity. It describes how mass and energy curve space-time, and how that curvature produces what we experience as gravity. Massive objects like stars and planets create curves in space-time. Other objects moving through that curved space-time follow paths determined by the curvature. We perceive those paths as the effects of gravitational attraction. But there's no force pulling objects together. They're simply following the natural contours of curved space-time. One consequence of this is that time itself is part of the physical universe. Time isn't some external stage on which events unfold. It's part of the structure of space-time itself. And if space-time had a beginning, then time had a beginning. There can be no time before the Big Bang because time itself began at the Big Bang. This is what physicists mean when they say asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because there is no north of the North Pole. North is a direction defined on Earth's surface. At the North Pole, every direction is south. Similarly, before is a temporal direction. It means earlier in time. But if time itself began at the Big Bang, there is no earlier. Every moment is after the Big Bang. The concept of before simply doesn't apply. Now, you might object. Surely something must have existed. Surely the Big Bang didn't just spontaneously appear from nothing. This is where we need to be very careful about what we mean by nothing. In everyday language, nothing means the absence of anything, empty space, void. But in physics, nothing is far more complicated. Let's start with what seems like the simplest kind of nothing, empty space. A perfect vacuum with absolutely nothing in it. No matter, no radiation, no energy, no particles. Just pure, empty space. You might think this is truly nothing, but according to quantum mechanics, it's not. Quantum mechanics is the theory that describes how particles behave at the smallest scales. It's one of the most successful theories in all of physics, tested and confirmed through countless experiments over the past century. And quantum mechanics tells us something very strange about empty space. It's not actually empty. Even in a perfect vacuum, with all matter and radiation removed, quantum fields still exist. Every type of particle has an associated quantum field that permeates all of space. There's an electromagnetic field, a field for electrons, fields for quarks, and so on. These fields exist everywhere, even in regions we'd call empty, and these quantum fields are constantly fluctuating. They're never perfectly still. Even in their lowest energy state, what we call the ground state or vacuum state, they're seething with activity. Virtual particles are constantly popping into and out of existence. An electron and a positron can spontaneously appear, exist for a tiny fraction of a second, and then annihilate each other and disappear. This happens everywhere, all the time. These aren't real particles, in the sense that they can be detected and measured. They exist for such a short time that they can't violate conservation of energy. The Heisenberg uncertainty principle allows energy to be borrowed from the vacuum for very brief periods. The shorter the time, the more energy can be borrowed. These virtual particles have real, measurable effects. They cause a tiny shift in the energy levels of hydrogen atoms, called the Lamb shift. They create a tiny attractive force between conducting plates called the Casimir effect. They contribute to the magnetic moment of the electron. We've measured these effects to extraordinary precision. They match the theoretical predictions from quantum field theory to better than 1 part in a billion in some cases. So empty space isn't really empty. It's filled with quantum fluctuations. Virtual particles appearing and disappearing. Quantum fields fluctuating around their ground state. This is the quantum vacuum, and it's the closest thing to nothing that exists in our universe. But it's not truly nothing. It's something. It has properties. It has energy, albeit the minimum possible energy. It can produce measurable effects. Now, here's where things get interesting. Some physicists have proposed that the universe itself could have emerged from a quantum fluctuation of the vacuum. The idea is that space-time itself is subject to quantum fluctuations. Just as particle-antiparticle pairs can pop into existence from the vacuum, perhaps an entire universe can. This sounds absurd. How can something as vast as the universe come from nothing? But remember, the early universe was incredibly small. At the very beginning, all of space might have been smaller than an atom, smaller than a proton, perhaps even smaller than the Planck length, which is about 10 to the minus 35 meters. That's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 laws of quantum mechanics apply not just to particles, but to space-time itself. And quantum mechanics allows for tunneling. Particles can tunnel through barriers that classical physics says they can't cross. An electron can tunnel through an insulator and appear on the other side. This happens in every computer chip, in every flash drive, in every piece of modern electronics. Similarly, the universe itself might have tunneled into existence. It might have spontaneously appeared from a quantum fluctuation, borrowing energy from the vacuum. Of course, a universe is far larger and more energetic than a single electron. How can the energy for an entire universe be borrowed from the vacuum? Here's the remarkable thing. The total energy of the universe might be zero. This sounds impossible, but it works because gravity has negative energy. Mass and radiation have positive energy. But the gravitational field has negative potential energy. When you add up all the positive energy from matter and radiation, and all the negative energy from gravity, the sum might cancel out exactly. The total energy of the universe could be precisely zero. If that's the case, then the universe doesn't need to borrow any net energy from the vacuum. It can spontaneously appear without violating conservation of energy. This idea was developed by several physicists in the 1980s and 90s, including Alexander Vilenkin, James Hartle, and Stephen Hawking. They worked out the mathematics of how a universe could tunnel into existence from nothing. Their equations describe what they call a quantum creation event, a spontaneous appearance of space-time and matter from the quantum vacuum. Now, this raises an obvious question. If the universe emerged from the quantum vacuum through a quantum fluctuation, where did the quantum vacuum come from? We've just pushed the question back one level. We've replaced the question of where the universe came from with the question of where quantum fields and the laws of quantum mechanics came from. This is a legitimate objection. We haven't explained everything. We've just explained how something with the properties of our universe could emerge from something with the properties of a quantum vacuum. But what about the quantum vacuum itself? What about the laws of physics? What about mathematics? Where did they come from? Here we reach the limits of science. Science is the process of explaining the observed universe using natural laws and mechanisms. It can tell us how the universe evolved from the Big Bang to the present. It can even tell us, at least in principle, how the Big Bang itself might have occurred. But when we ask where the laws of physics came from, we're asking a question that might be beyond the scope of science. Perhaps the laws of physics just are. Perhaps they're fundamental features of reality that don't require further explanation. Perhaps asking why the laws of physics have the form they do is like asking why 2 + 2 = 4. It just is. It's a necessary truth about mathematics, and mathematics is what it is. Or perhaps there's a deeper level of explanation we haven't discovered yet. Perhaps there's a more fundamental theory that explains why the laws of physics have the form they do. String theory and loop quantum gravity are attempts to find such a theory, but they're incomplete and speculative. Some physicists have proposed the multiverse, the idea that our universe is just one of many universes, perhaps infinitely many, each with different laws of physics. In this view, the laws of physics in our universe aren't unique or special. They're just one possibility among many. We observe the particular laws we do because we exist in a universe where those laws allow for the formation of galaxies, stars, planets, and life. Universes with different laws might not be able to produce complex structures or conscious observers. This is called the anthropic principle. We shouldn't be surprised that we observe a universe with laws that permit our existence, because if the laws were different, we wouldn't be here to observe anything. The multiverse idea is controversial. Many physicists love it. Many others think it's unscientific because other universes, by definition, can't be observed or tested. If we can never detect or interact with other universes, then the multiverse hypothesis isn't really a scientific theory. It's more like metaphysics, philosophy rather than physics, but the debate continues. Let's return to the question of what happened at the Big Bang itself. When we use Einstein's equations to describe the early universe, we run into a problem. If we run the expansion backward in time, the universe gets denser and denser, hotter and hotter. Eventually, we reach a point where the density becomes infinite, the temperature becomes infinite, and the curvature of space-time becomes infinite. This is called a singularity. At the singularity, the equations break down. They give nonsensical results. Infinity divided by infinity. 0 divided by 0. The mathematics stops working. This tells us something important. It tells us that general relativity, Einstein's theory of gravity and space-time, can't be the complete story. The theory is extremely accurate for describing stars, galaxies, and the large-scale structure of the universe. But when we try to apply it to the very beginning of the universe, to times earlier than about 10 to the minus 43 seconds after the Big Bang, it fails. This timescale is called the Planck time. It's the time it takes light to travel one Planck length. Below the Planck scale, quantum effects on space-time become important. Space-time itself becomes grainy and discontinuous. The smooth fabric of space-time, described by general relativity, breaks down. We need a quantum theory of gravity to describe what happens, and we don't have one. This is one of the biggest unsolved problems in theoretical physics. General relativity describes gravity as the curvature of space-time. It works beautifully for large objects like planets and stars. Quantum mechanics describes how particles behave at the smallest scales. It works beautifully for atoms and subatomic particles, but the two theories are mathematically incompatible. They can't both be exactly correct. When you try to combine them, when you try to apply quantum mechanics to gravity and space-time, the equations give infinite results that can't be removed. Physicists have been trying to solve this problem for decades. String theory is one attempt. It proposes that fundamental particles aren't point-like, but are instead tiny vibrating strings of energy. Different vibration modes correspond to different particles. In string theory, gravity emerges naturally. One of the vibration modes corresponds to the graviton, the hypothetical particle that carries the gravitational force. String theory also requires extra dimensions of space beyond the 3 we experience. Depending on the version, it requires either 10 or 11 total dimensions. The extra dimensions are compactified, curled up so tightly that we don't notice them. String theory is mathematically beautiful and has inspired enormous amounts of research, but it hasn't made any testable predictions yet. The energy scales where string theory effects become important are far beyond what we can reach with particle accelerators. We can't test it experimentally, at least not with current technology. Loop quantum gravity is another approach. It proposes that space-time itself is quantized. Just as energy comes in discrete packets called quanta, space-time comes in discrete chunks. Space isn't infinitely divisible. At the smallest scales, it's made of tiny loops or networks of loops. Loop quantum gravity suggests that the Big Bang singularity might not exist. Instead of density and temperature becoming infinite, they reach a maximum value and then bounce. The universe might have been contracting before the Big Bang, then reached a minimum size and bounced back into expansion. This is called a big bounce instead of a Big Bang. If the Big Bounce picture is correct, then time didn't begin at the Big Bang. There was a before, a previous phase of cosmic history when the universe was contracting. But this is speculative. Loop quantum gravity, like string theory, hasn't been tested experimentally. We don't know if it's correct. Other approaches exist too. Causal dynamical triangulations, asymptotic safety, causal sets. Each proposes a different way to quantize gravity. Each has its advocates and its problems. The truth is, we don't have a quantum theory of gravity yet, and until we do, we can't answer the question of what happened at the Big Bang with certainty. We can describe the universe from about 1 second after the Big Bang onward with great confidence. Our theories match observations to extraordinary precision. But the very first moment, the first tiny fraction of a second, is hidden behind a veil of ignorance. Now, there's another piece of this puzzle that needs to be addressed. Cosmic inflation. Inflation is a theory proposed in the early 1980s by Alan Guth and others. It suggests that in the very early universe, there was a brief period when space expanded exponentially fast. In a tiny fraction of a second, a region smaller than a proton inflated to the size of a grapefruit or larger. The expansion factor was at least 10 to the 26. That's a 1 followed by 26 zeros. During inflation, space was expanding faster than the speed of light. Wait, doesn't relativity say nothing can travel faster than light? Yes, but that applies to things moving through space. Space itself can expand at any rate. There's no speed limit on the expansion of space. Inflation solves several problems in cosmology. It explains why the universe looks so uniform in all directions. Regions of space that are now billions of light years apart were once close enough to interact and reach the same temperature. Then inflation stretched them apart so fast that they're now beyond each other's observable horizons. Inflation also explains why space appears to be flat rather than curved. Any initial curvature would have been stretched out by the exponential expansion. It's like inflating a balloon. When the balloon is small, the curvature of its surface is obvious. But if you inflate it to an enormous size, a small patch of the surface looks flat. Inflation also explains the origin of structure in the universe. During inflation, quantum fluctuations in the density of energy were stretched to cosmic scales. These tiny variations became the seeds for galaxies and clusters of galaxies. We can see the imprint of these quantum fluctuations in the cosmic microwave background radiation. The tiny temperature variations we observe match the predictions of inflation. This is strong evidence that inflation actually happened. But inflation doesn't solve the singularity problem. It just pushes it back. Inflation requires very specific initial conditions. You need a particular kind of energy field, called the inflaton field, to drive the exponential expansion. You need the universe to start in a special state for inflation to work. Where did those conditions come from? If you trace inflation backward in time far enough, you still reach a singularity where the equations break down. So inflation describes what happened in the first tiny fraction of a second after the Big Bang. But it doesn't tell us what happened at the Big Bang itself. It doesn't explain the origin of time or space or the laws of physics. Some versions of inflation, called eternal inflation, suggest that once inflation starts, it never completely stops. In most regions of space, inflation ends and a normal universe like ours forms. But in other regions, inflation continues. And in those regions, random quantum fluctuations can cause new regions to stop inflating, forming new pocket universes. This process continues forever, creating an infinite number of pocket universes, each potentially with different laws of physics. Our observable universe would be just one tiny bubble in an eternally inflating multiverse. This is a mind-bending idea with profound implications. If eternal inflation is correct, then the Big Bang that created our universe wasn't the beginning of everything. It was just the beginning of our particular pocket universe. The multiverse as a whole has been inflating forever, with no beginning. But even eternal inflation doesn't completely avoid the need for a beginning. Some mathematical theorems, particularly the Border-Guth-Vilenkin theorem, proved in 2003, suggest that even an eternally inflating multiverse must have had a beginning. You can't have an infinite past of exponential expansion without running into mathematical inconsistencies. So we're back to the same question. What happened at the beginning? Let's try a different approach. Let's think carefully about what we mean by nothing. We've already seen that empty space isn't truly nothing because quantum fields exist. But what if we remove even those? What if we imagine a state with no space, no time, no quantum fields, no laws of physics, no mathematics, no anything? True, absolute nothing. Philosophers call this metaphysical nothingness. Can we even conceive of such a state? Most philosophers think not. the concept might be incoherent. To conceive of something, even nothing, you need to attribute properties to it. But if you attribute properties, it's not truly nothing. It's something with those properties. True nothingness would have no properties at all. Not even the property of existing or not existing. It's a concept that might not make logical sense. There's also a practical problem. We've never observed true nothingness. Everything we've ever studied has properties. Even the vacuum of space has quantum fields. So we have no empirical basis for understanding what nothing would be like. Some philosophers argue that true nothingness is unstable. If nothing existed, there would be no laws of physics to prevent something from appearing. The very concept of nothing contains the seeds of something. This is a philosophical argument, not a scientific one. But it's interesting. If nothing is inherently unstable, then the universe's existence might not require an external cause. It might be a necessary consequence of logic itself. Other philosophers take the opposite view. They argue that nothing is the natural state. Something requires explanation. Why is there something rather than nothing? This has been called the fundamental question of metaphysics. The physicist and philosopher Lawrence Krauss wrote a book titled A Universe from Nothing. He argues that physics has answered this question. The universe can arise from quantum fluctuations of the vacuum. No supernatural creator needed. But critics pointed out that the quantum vacuum isn't truly nothing. It's a physical state with definite properties governed by the laws of quantum field theory. So Krauss didn't really explain how you get something from nothing. He explained how you get our universe from a quantum vacuum. That's still impressive and important. But it's not the same as explaining how you get something from absolute nothing. Krauss's response is that absolute nothing might be impossible. The laws of physics might be necessary features of reality. They might exist even in the absence of a universe. In that case, the quantum vacuum is the closest thing to nothing that can exist, and our universe can arise from that. This brings us to a deep question about the nature of mathematics and physical law. Are the laws of physics invented or discovered? Do they exist independently of the universe, or are they properties of the universe? Platonists believe that mathematical structures exist eternally and independently of physical reality. The number pi doesn't depend on whether any circles exist in the universe. It's a necessary truth about mathematics. Similarly, the laws of physics might be necessary truths, features of mathematical reality that exist whether or not a physical universe exists. In this view, when physicists discover a new law, they're not inventing it. They're uncovering something that was already true in some abstract sense. Other philosophers disagree. They think mathematics is a human invention, a language we created to describe patterns we observe. The laws of physics are descriptions of how the universe behaves, not independent entities. This debate has profound implications for our question about the origin of the universe. If laws of physics exist independently, then they can explain the origin of the universe. The universe might be a necessary consequence of mathematical law, but if laws of physics are just descriptions of the universe, then they can't explain the universe's origin. They're part of what needs to be explained. Let's consider another possibility. Maybe the question of what came before the Big Bang is simply meaningless. Not meaningless in the sense that we don't know the answer, but meaningless in the sense that the question itself doesn't correspond to anything in reality. It's like asking what happens when an unstoppable force meets an immovable object. The question seems to make grammatical sense, but it's logically incoherent. By definition, if a force is unstoppable, there can be no immovable objects. If an object is immovable, there can be no unstoppable forces. The question presumes a situation that's logically impossible. Similarly, asking what came before the Big Bang presumes that time extended before the Big Bang. But if time itself began at the Big Bang, there is no before. The question is based on a false assumption about the nature of time. Stephen Hawking made this point using an analogy. He compared asking what's before the Big Bang to asking what's south of the South Pole. At the South Pole, every direction is north. The concept of south doesn't apply. Similarly, at the Big Bang, every direction in time is forward. The concept of before doesn't apply. Hawking developed a model of the universe's origin with Jim Hartle called the no-boundary proposal. In their model, time near the Big Bang becomes similar to space. The distinction between time and space blurs. Instead of time having a beginning, it curves back on itself, forming a smooth surface with no edge or boundary. It's like the surface of Earth. If you travel south, you eventually reach the South Pole. You don't fall off an edge. You just reach a point where south is no longer a meaningful direction. Similarly, if you go backward in time, you eventually reach the Big Bang. You don't encounter a beginning or a singularity. You just reach a point where earlier is no longer a meaningful direction. Time transitions smoothly into space. This model requires imaginary time, a mathematical tool from quantum mechanics. It's not clear whether imaginary time corresponds to anything physically real or if it's just a mathematical trick, but the no-boundary proposal suggests a way to avoid the question of what came before. There is no before, not because time began abruptly, but because time gradually ceases to be time-like as you approach the Big Bang. All of these ideas are speculative. We don't have the empirical evidence to determine which, if any, is correct. We might never have such evidence. The conditions at the Big Bang involved energies far beyond what we can achieve in particle accelerators. The Planck energy, where quantum gravity effects become important, is about 10 to the 19 billion electron volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 trillion electron volts. That's a million times less than the Planck energy. We'd need an accelerator the size of the galaxy to reach Planck energies. That's not going to happen. So our ability to test theories about the Big Bang directly is extremely limited. We have to rely on indirect evidence. Observations of the cosmic microwave background radiation, the large-scale structure of galaxies, the abundances of light elements, gravitational waves from the early universe, if we can detect them. These observations can constrain theories, but they can't give us a complete picture of what happened at the very beginning. There's also the question of whether the universe is unique. Is our universe the only one that exists, or is it one of many? The multiverse hypothesis suggests there are other universes, perhaps infinitely many. Some versions of string theory predict 10 to the 500 different possible universes, each with different laws of physics. If the multiverse exists, then asking what came before the Big Bang might be asking the wrong question. Perhaps universes are constantly being created from the quantum vacuum. Our Big Bang was just one event among many. The multiverse as a whole might have no beginning. New universes might be appearing all the time, each with its own Big Bang, its own timeline. But this raises new questions. Where does the multiverse come from? What are the laws that govern the creation of new universes? We've just pushed the question back another level. Some physicists embrace this. They argue that there's no final answer. Every explanation requires assumptions, and those assumptions themselves require explanation. It's explanations all the way down. Others find this unsatisfying. They hope for a theory of everything, a final complete description of reality that requires no further explanation. Whether such a theory is possible is unknown. Let's step back and consider what we've learned. The universe began about 13,800 million years ago in an event we call the Big Bang. Space and time came into existence then. Everything we can observe traces back to that moment. The evidence for this is overwhelming and comes from multiple independent sources. When we ask what existed before the Big Bang, we face deep problems. According to general relativity, time itself began at the Big Bang. There is no before in the normal sense of the word. Quantum mechanics suggests that empty space isn't truly empty, but is filled with quantum fluctuations. The universe might have emerged from a quantum fluctuation of the vacuum. This explains how the Big Bang could have occurred, but it doesn't explain where the vacuum and the laws of quantum mechanics came from. We need a quantum theory of gravity to fully understand the Big Bang. We don't have one yet, despite decades of effort. String theory and loop quantum gravity are promising but incomplete. Cosmic inflation explains many features of the universe, but doesn't explain the ultimate origin. Eternal inflation suggests a multiverse, but even that seems to require a beginning. Philosophers have debated the concept of nothing for millennia. True absolute nothingness might be logically incoherent, or it might be unstable, naturally giving rise to something. The laws of physics might be necessary features of reality, or they might be contingent facts about our particular universe. This determines whether a purely physical explanation for the universe's existence is possible. Some physicists think the question of what came before the Big Bang is meaningless. It's like asking what's north of the North Pole. Time didn't exist before the Big Bang, so before doesn't apply. Others think there might have been a before, but we need new physics to describe it. Perhaps time is emergent rather than fundamental. Perhaps it arises from some deeper structure that doesn't involve time. The honest answer is that we don't know. We have sophisticated theories and intriguing ideas, but no definitive answers. The origin of the universe remains one of the deepest mysteries in science, and it might remain a mystery forever. Some questions might be beyond the reach of science. Not because we're not smart enough or don't have good enough technology, but because the questions themselves might not have answers that can be tested empirically. If we can never observe what happened before the Big Bang, because there is no before, then we can't use the scientific method to investigate it. We can develop mathematical models and philosophical arguments, but we can't do experiments. Science works by making predictions, testing them against observations, and refining theories based on the results. If a theory makes no testable predictions, it's not really science. It's metaphysics. That doesn't mean it's worthless or wrong. It just means it's a different kind of inquiry. Philosophy rather than physics. Some physicists are comfortable with this. They acknowledge that questions about the ultimate origin of everything might be inherently philosophical. Science can take us back to the Big Bang, but perhaps no further. Others hold out hope for a theory of everything that explains its own existence. A self-contained mathematical structure that gives rise to the universe and the laws of physics, with no need for external explanation. Whether such a theory is possible is unknown. Roger Penrose has suggested that the Big Bang might have been preceded by a previous cosmic eon. In his conformal cyclic cosmology, the universe goes through infinite cycles. Each eon begins with a Big Bang and ends when the universe has expanded so much that all matter has decayed and only radiation remains. At that point, with no matter left to define scale, the infinite future of one eon can be mathematically matched to the Big Bang of the next eon. Time continues through the transition, but in a strange way, this model suggests that our Big Bang was actually the end of a previous universe. Time didn't begin at the Big Bang. It continued from before, but in such a transformed state that we can't observe or access information from the previous eon. Penrose has claimed to see evidence for this in the cosmic microwave background radiation, patterns that might be the imprints of black hole collisions from the previous eon. Most cosmologists are skeptical. The patterns Penrose identifies could be statistical fluctuations, and the model requires assumptions that seem contrived. But it's an interesting idea that shows there are alternatives to the standard story. Another possibility is that our universe is a simulation. If we're living in a computer simulation created by some advanced civilization, then our Big Bang would just be the start of the simulation. It wouldn't represent the origin of everything, just the origin of our simulated reality. The civilization running the simulation would exist outside our universe, in some larger reality, with its own physical laws. This idea has gained surprising traction in recent years. Some physicists and philosophers take it seriously. They point out that if civilizations eventually develop the ability to run detailed simulations of universes, and if they run many such simulations, then, statistically, we're more likely to be in a simulation than in the base reality. If there's one base reality and a million simulations, you have only a 1 in a million chance of being in the base reality. But this argument has problems. We have no evidence that simulating an entire universe is possible. It might require more computational resources than can exist in any universe. And the argument assumes that simulated beings would be conscious and have subjective experiences. We don't know if that's possible. Most physicists don't take the simulation hypothesis seriously. It's not testable, and there's no evidence for it. It's interesting to think about, but not useful for understanding physics. Let's consider one more possibility. Maybe the question of what came before the Big Bang doesn't have a single answer. Maybe the universe is fundamentally probabilistic. Quantum mechanics tells us that reality isn't deterministic at the smallest scales. Particles don't have definite positions or velocities until they're measured. They exist in superpositions, being in multiple states at once. When you measure a particle, you force it to choose one state, but before measurement, all possible states coexist. Some interpretations of quantum mechanics suggest this applies to the entire universe. The universe might be in a superposition of many different states, including different histories. In this view, there isn't one definite answer to what came before the Big Bang. There are many possible answers, and all of them are real in some sense. Our universe is just one branch of a vast quantum multiverse where every possible history exists. This is the many worlds interpretation of quantum mechanics. It's controversial and hard to test, but some physicists find it elegant. It suggests that the universe doesn't have a single origin story. It has all possible origin stories, playing out in parallel realities. All of these ideas, the quantum creation event, the Big Bounce, eternal inflation, the no-boundary proposal, conformal cyclic cosmology, the simulation hypothesis, the many worlds interpretation, are attempts to answer the question of what came before the Big Bang. None have been proven. All are speculative to varying degrees. But they show that physicists are thinking deeply about these questions, exploring every possible avenue. The truth is, we're at the frontier of knowledge. We understand the universe from about 1 second after the Big Bang onward with extraordinary precision. But the very first moment, the origin of space and time itself, remains mysterious. We might solve this mystery in the coming decades if we develop a quantum theory of gravity and find ways to test it. Or we might find that the question lies permanently beyond the reach of science, in the realm of philosophy and metaphysics. Either way, it's one of the most profound questions humans have ever asked. What came before everything? Where did it all come from? Why is there something rather than nothing? These questions have fascinated people for thousands of years. Every culture has creation myths and origin stories. For most of history, these questions belong to religion and philosophy. Science couldn't address them. But in the 20th century, physics made enormous progress. Einstein's relativity, quantum mechanics, the discovery of the Big Bang, the cosmic microwave background radiation, all of this brought the origin of the universe within the scope of scientific investigation. We went from having no idea about the universe's history to understanding it in extraordinary detail. We can describe the first few minutes after the Big Bang, when nuclear fusion created the light elements. We can describe the first few 100,000 years, when atoms formed and light could travel freely for the first time. We can describe the formation of the first stars, the first galaxies, the large-scale structure of the universe. We can trace cosmic history forward from the Big Bang to the present with confidence, but we can't yet trace it back to the very beginning. We can't yet answer the question of what came before, or whether before even makes sense. This is humbling. After all our progress, after developing theories as profound as general relativity and quantum mechanics, we still don't understand the ultimate origin of reality. We might never understand it completely, but that's part of what makes science exciting. There are always new frontiers, always deeper questions. Every answer leads to new questions. We've learned that nothing isn't really nothing. Empty space is filled with quantum fluctuations. We've learned that time might not be fundamental, but emergent. We've learned that the universe might be one of many in a vast multiverse. We've learned that the Big Bang might not have been the beginning of everything, just the beginning of our particular universe. We've learned that some of our intuitions about time and existence might be wrong. Time doesn't have to extend backward forever. It can have a beginning without there being anything before. We've learned that mathematics and physical law might be deeply connected, perhaps even identical in some sense. We've pushed our understanding back to unimaginable extremes, to fractions of a second after the Big Bang, to energies billions of times higher than anything we can create in laboratories, to distances billions of light years across, to times billions of years in the past. And we've discovered that the universe is far stranger than anyone imagined. Space and time are not absolute, but relative. Matter and energy are equivalent. Particles can tunnel through barriers. Empty space isn't empty. The universe is expanding faster and faster. Most of the universe is invisible, made of dark matter and dark energy that we don't understand. And at the beginning of it all, there was something. Not nothing, but something. A quantum fluctuation, perhaps. An instability in the vacuum. A mathematical necessity. A bounce from a previous universe. A simulation starting up. A superposition of all possible beginnings. Or simply the origin of time itself, with no before. We don't know which of these is correct. Maybe none of them are. Maybe the truth is something we haven't thought of yet. But we keep asking the questions, keep developing new theories, keep pushing the boundaries of knowledge, because these questions matter, not for any practical purpose. Understanding the Big Bang won't help us build better computers or cure diseases, but it matters because we're curious, because we want to know where we came from, because we want to understand the nature of reality, because humans have always looked up at the night sky and wondered, and now we have the tools to actually investigate these questions scientifically. We have telescopes that can see the cosmic microwave background radiation, light from when the universe was 380,000 years old. We have particle accelerators that can recreate conditions from microseconds after the Big Bang. We have mathematical theories that let us calculate what happened in those first moments. We don't have all the answers yet. We might never have all the answers, but we've come remarkably far. In just a century, we went from not knowing that other galaxies exist to understanding the history of the entire universe. We went from thinking the universe was eternal and unchanging to knowing it had a beginning and is expanding. We went from complete ignorance about the universe's origin to having detailed, testable theories. That's extraordinary progress. And it shows no sign of slowing down. New telescopes are being built, that will observe even earlier times in the universe's history. New particle accelerators are being designed that will probe higher energies. New theories are being developed that might finally unify quantum mechanics and gravity. In the coming decades, we might answer some of these questions definitively. We might discover the quantum theory of gravity that describes the Big Bang. We might find evidence for the multiverse. We might determine whether time is fundamental or emergent. Or we might find that these questions are unanswerable, that they lie permanently beyond the reach of observation and experiment. That would be disappointing, but it would also be a kind of answer. It would tell us about the limits of scientific knowledge. Either way, the quest continues. The quest to understand where we came from, what came before, why there's something rather than nothing. It's one of the most profound endeavors in human history. And tonight, you've been part of it. You've explored the deepest questions about existence. Now let's dig even deeper into what this all means. When we talk about the quantum vacuum and virtual particles, we need to understand just how strange this really is. The vacuum isn't passive. It's not just sitting there doing nothing. It's actively creating and destroying particles constantly. Every cubic centimeter of empty space is a seething cauldron of activity. Electron-positron pairs appear from nothing, exist for about 10 to the minus 21 seconds, and vanish. Quark-antiquark pairs do the same. Even photons, particles of light, spontaneously appear and disappear. This happens everywhere, all the time, throughout the entire universe. It's not hypothetical or theoretical. We can measure the effects. The Casimir effect is one of the most striking demonstrations. If you place two uncharged metal plates very close together in a vacuum, they attract each other. There's no electromagnetic force between them. They're not charged. But they still attract. Why? Because the quantum vacuum between the plates is different from the vacuum outside the plates. Virtual particles with wavelengths larger than the gap between the plates can't exist in the gap, but they can exist outside. This creates a difference in vacuum energy. More vacuum energy pushes on the plates from outside than from inside. The result is a net force pushing the plates together. This force is incredibly tiny. For plates separated by 1 micrometer, which is 1/1000th of a millimeter, the force is only about 1/100000th of a newton per square meter, but it's been measured precisely in laboratories. The measurements match the theoretical predictions. This proves that the quantum vacuum has real, measurable energy. Empty space isn't truly empty. Now, here's where it gets interesting for cosmology. If the quantum vacuum has energy, and if that energy is uniform throughout space, then it acts like what Einstein called the cosmological constant. It creates a kind of anti-gravity that causes space itself to expand. This might be what we observe as dark energy. Dark energy is the mysterious force causing the universe's expansion to accelerate. We discovered it in 1998 by observing distant supernovae. These exploding stars were farther away than expected based on their brightness and redshift. The only explanation is that the expansion of the universe is speeding up. Something is pushing space apart against the pull of gravity. We call this something dark energy, and it makes up about 68% of the total energy content of the universe. The simplest explanation for dark energy is vacuum energy, the energy inherent in empty space itself. But there's a problem. When physicists calculate how much vacuum energy there should be based on quantum field theory, they get a number that's about 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. This is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. Why is the vacuum energy so much smaller than theory predicts? Nobody knows. Some physicists think there must be a mechanism that cancels out most of the vacuum energy, leaving only a tiny remainder. Others think our understanding of quantum field theory is incomplete. Still others invoke the anthropic principle, arguing that only universes with small vacuum energy can form galaxies and stars and planets and life. So we shouldn't be surprised to find ourselves in such a universe. But this feels like giving up on finding a real explanation. The cosmological constant problem is closely connected to the question of what existed before the Big Bang. If vacuum energy can cause space to expand exponentially, as in cosmic inflation, then perhaps vacuum energy was also responsible for creating the universe in the first place. Maybe the Big Bang was triggered by a quantum fluctuation in some pre-existing vacuum, but this just pushes the question back. Where did that vacuum come from? What determined its properties? Why does it have the particular amount of energy it does? Let's think more carefully about the nature of time. In our everyday experience, time seems to flow from past to future. We remember yesterday, but not tomorrow. We can affect the future, but not the past. Causes precede effects. This directionality of time is called the arrow of time, and it's one of the deepest puzzles in physics. Here's the puzzle. The fundamental laws of physics are time-symmetric. If you take any physical process described by quantum mechanics or relativity and run it backward in time, you get another valid physical process. The equations work equally well in both directions. There's nothing in the fundamental laws that distinguishes past from future, yet our experience is profoundly asymmetric. We clearly know the difference between past and future. Why? The answer has to do with entropy and the second law of thermodynamics. Entropy is a measure of disorder or randomness. The second law states that entropy always increases in isolated systems. Things naturally become more disordered over time. An ice cube in warm water melts. Heat flows from hot objects to cold objects. A broken egg doesn't spontaneously reassemble itself. These processes are irreversible. They define a direction of time. But why does entropy increase? Why were things more ordered in the past than they are now? The answer traces back to the Big Bang. The early universe was in an extremely low entropy state. Matter and energy were distributed almost uniformly, with only tiny fluctuations. This seems like high entropy, because everything was mixed together. But actually, it's very low entropy when you account for gravity. For a system dominated by gravity, a uniform distribution is highly ordered. High entropy would mean everything clumped together into black holes. So the Big Bang started the universe in a very special, low entropy state. Ever since then, entropy has been increasing. Gravity pulls matter together into clumps. Stars form and burn their fuel. Black holes grow. The universe becomes more disordered at a fundamental level. This increase in entropy from the initial low entropy state is what gives time its arrow. It's why we remember the past and not the future. It's why we age. It's why processes are irreversible. But this just shifts the question. Why did the Big Bang start the universe in such a low entropy state? Why wasn't the initial state maximally random and disordered? If the universe began from a random quantum fluctuation, you'd expect it to start with high entropy. The fact that it didn't requires explanation. Roger Penrose has emphasized this problem. He calculated that the odds of a universe like ours emerging randomly from a fluctuation are incredibly tiny, about 1 in 10 to the power of 10 to the power of 123. That's a number so large it's hard to even express. The number of possible high-entropy states vastly outnumbers the low-entropy states like our Big Bang. So if the universe just randomly appeared, it should almost certainly have appeared in a high-entropy state. The fact that it didn't suggests the Big Bang wasn't random. There must be some principle or mechanism that selected for a low-entropy beginning. Some physicists think cosmic inflation solves this problem. Inflation would have taken a small region of space and stretched it exponentially. Any initial irregularities or entropy would have been smoothed out, The universe after inflation would naturally be in a low entropy state, but inflation itself requires special initial conditions. You need the inflaton field to start in the right configuration, so you're still left with the question of why those initial conditions existed. Other physicists think the answer lies in the multiverse. Maybe there are countless universes with different initial conditions. Most have high entropy and don't form interesting structures, but a tiny fraction, through random chance, start with low entropy. Those are the ones where life can exist and observers can ask questions. We find ourselves in a low entropy universe because that's the only kind where we could exist. This is an application of the anthropic principle. It's controversial because it seems to give up on finding a deeper explanation, but it might be the truth. Maybe there is no deeper explanation. Maybe the universe's initial state is just a brute fact about reality. Let's explore another aspect of this question: the nature of causality. We're used to thinking in terms of cause and effect. Every event has a cause. The cause comes before the effect in time. If we trace causes backward, following the chain of causation, we eventually reach the Big Bang. But what caused the Big Bang? If there's no time before the Big Bang, the concept of causation breaks down. A cause must come before its effect. But there is no before, so the Big Bang can't have a cause in the normal sense. Does this mean the Big Bang was uncaused? That it just happened for no reason? Many people find this deeply unsatisfying. Everything in our experience has a cause. The principle that every event has a cause, called the principle of sufficient reason, has been a cornerstone of philosophy since ancient times. If the Big Bang was uncaused, it violates this principle. But maybe the principle is wrong. Maybe not everything has a cause. Quantum mechanics already tells us that some events are uncaused. Radioactive decay, for instance. An atom of uranium can sit stable for billions of years and then suddenly decay. There's no cause for why it decayed at that particular moment, rather than earlier or later. It's truly random. Quantum mechanics gives us probabilities, not certainties. We can calculate that a given uranium atom has a 50% chance of decaying within 4.5 billion years, but we can't predict exactly when it will decay. The decay event has no cause. It just happens. If uncaused events can occur at the quantum level, maybe an uncaused event can occur at the cosmic level. Maybe the Big Bang just happened. No reason, no prior cause, just a quantum fluctuation that gave rise to a universe. This is philosophically radical. It overturns thousands of years of thinking about causation and explanation, but it might be the truth. Alternatively, maybe causation works differently at the cosmic scale. Maybe time is emergent rather than fundamental. Some theories in quantum gravity suggest that space-time isn't the most basic level of reality. Something more fundamental underlies it. In loop quantum gravity, space-time is built from discrete loops or networks at the Planck scale. In string theory, space-time emerges from the interactions of strings. In some versions of quantum mechanics, time emerges from the entanglement between quantum systems. If time is emergent, then asking about causation at the level of the Big Bang might not make sense. Causation is a concept that applies within space-time, not to space-time itself. The universe didn't begin in time. Time began with the universe. Causation requires time, so causation doesn't apply to the origin of time. This is consistent with the no-boundary proposal. If time smoothly transitions into space near the Big Bang, with no sharp boundary or beginning, then there's no moment that needs a cause. The universe just is, as a complete four-dimensional structure. All moments exist together in the block universe picture of relativity. From this perspective, asking why the universe exists is like asking why mathematics exists. It's a category error. Mathematics doesn't exist in time or space. It's not the kind of thing that needs a cause. It's just true, independent of physical reality. Maybe the universe is the same. Maybe it's a necessary feature of reality, existing timelessly as a complete mathematical structure. This brings us to mathematical Platonism, the idea that mathematical structures exist independently of physical reality. The number pi doesn't depend on whether any circles exist. It's a necessary truth about the geometry of flat space. Max Tegmark has proposed a radical version of this idea called the mathematical universe hypothesis. He suggests that physical reality is a mathematical structure, not just described by mathematics, but actually identical to it. The universe is mathematics. In this view, asking why the universe exists is asking why mathematics exists, and mathematics doesn't need a cause or explanation. It's necessarily true by logic alone. 2 + 2 = 4, not because of any physical law, but because that's what those symbols mean. Similarly, the laws of physics might be necessary truths about the structure of reality. They couldn't be any other way. The universe couldn't not exist. This is a bold claim. Most physicists don't accept it. They think the laws of physics are contingent facts about our particular universe, not necessary truths. But it's an interesting idea that shows how deeply these questions cut. Are the laws of physics discovered or invented? Are they features of reality or descriptions of reality? This philosophical question has practical implications for our topic. If laws of physics are necessary features of reality, then perhaps the universe's existence is also necessary. There couldn't not be a universe. The Big Bang couldn't not have happened. Asking what came before is meaningless, because there's no possible state of affairs without a universe. But if laws of physics are contingent, then the universe's existence needs explanation. We need to ask why these laws, rather than others. Why this universe, rather than no universe? The question of what came before the Big Bang leads inevitably to these deep philosophical issues. Let's consider the perspective of different theories of time. Philosophers distinguish between two views. The A theory, also called presentism, says that only the present moment exists. The past no longer exists, and the future doesn't exist yet. Time flows from past to future, and now is objectively real. The B theory, also called eternalism, says that all moments exist equally. Past, present, and future are all real. They're just different locations in the four-dimensional structure of space-time. Time doesn't flow. It's more like a dimension of space. Einstein's relativity supports the B theory. Relativity shows that simultaneity is relative. Events that are simultaneous in one reference frame aren't simultaneous in another. There's no objective present moment that all observers agree on. This makes sense if all moments exist equally, as in the B theory. It's hard to reconcile with the A theory, where only the present exists. If the B theory is correct, then the Big Bang isn't something that happened in the past. It's a location in space-time, specifically the location where the time coordinate reaches its minimum value. Asking what came before the Big Bang is like asking what's on the other side of a boundary. If space-time is finite in the time direction, with the Big Bang as its edge, then there simply is nothing before. Not because time extends back to the Big Bang and stops, but because the Big Bang is where space-time ends. There's no more space-time in that direction. If the A theory is correct, things are different. Time really does flow from past to future. The present is objectively real. The Big Bang was an event that occurred about 13,800,000,000 years ago. Before that event, time didn't exist. Time came into being with the Big Bang. This raises the question of how something can come into being if there's no time for it to come into being in. It seems paradoxical. How can time begin if there's no time for beginning to occur? This is one reason many physicists prefer the B theory. It avoids these paradoxes about the beginning of time. But the B theory has its own problems. It seems to deny our fundamental experience of time flowing. It makes the passage of time an illusion. Most physicists think the B theory is correct, or at least closer to the truth than the A theory. But the debate continues. Now, let's think about the existential implications of all this. If the universe came from nothing, if it was an uncaused quantum fluctuation, what does that mean for meaning and purpose? Many people find the idea troubling. If the universe is just a random accident, doesn't that make everything meaningless? If we're just collections of particles that happen to arrange themselves into conscious beings through blind physical processes, do our lives have value? These are philosophical and religious questions, not scientific ones. Science can tell us how the universe began, but it can't tell us whether that beginning has meaning or purpose. That's outside the scope of science. But it's worth thinking about. Some people find the scientific picture liberating. We're not here for any externally imposed purpose. We create our own meaning. Our lives have whatever purpose we choose to give them. Others find it depressing or nihilistic. If we're just accidents, why does anything matter? There's no one right answer to these questions. Different people will respond differently based on their values and temperaments, but understanding the physics doesn't force any particular philosophical or emotional response. You can accept that the universe emerged from a quantum fluctuation and still find life meaningful and valuable. The two aren't incompatible. What about the fine-tuning problem? This is another deep issue related to the origin of the universe. The laws of physics contain several fundamental constants: the strength of gravity, the charge of the electron, the mass of the proton, the speed of light, and many others. These constants have specific values in our universe, but as far as we know, they could have had different values. There's nothing in current physics that explains why they have the values they do. What's striking is that if these constants were slightly different, the universe would be radically different. Stars wouldn't form. Atoms wouldn't be stable. Chemistry wouldn't work. Life as we know it would be impossible. For example, if the strong nuclear force were just 2% stronger, protons would bind together so tightly that stars would burn out quickly. If it were 2% weaker, atomic nuclei would fall apart. Either way, no chemistry, no life. If gravity were slightly stronger, stars would burn out too fast for life to evolve. Slightly weaker, and stars wouldn't ignite at all. The range of values compatible with life is extremely narrow. This is called fine-tuning. The universe appears to be fine-tuned for life. There are three main responses to this observation. First, maybe it's just a coincidence. The constants happen to have life-permitting values. We're lucky. Most physicists find this unsatisfying. The odds against a randomly selected universe being life-permitting are astronomical. It seems like too much of a coincidence. Second, maybe there's a deeper theory that explains why the constants have the values they do. Maybe they're not arbitrary at all, but necessary consequences of more fundamental principles. This is what physicists hope to find. A theory of everything that would explain all the constants in terms of something more basic. String theory promises to do this, but hasn't delivered yet. Third, maybe there's a multiverse with different constants in different regions. Most regions aren't life-permitting, but some are, purely by chance. We observe a life-permitting universe because that's the only kind where observers can exist. This is another application of the anthropic principle. The multiverse hypothesis is popular among cosmologists. Eternal inflation naturally produces a multiverse. Different pocket universes can have different vacuum states, and these different vacuum states can correspond to different effective laws of physics and different values for the constants. If this is correct, then fine-tuning isn't surprising. It's inevitable that some universes would be life-permitting. We happen to be in one of them. But critics argue that the multiverse hypothesis is unscientific because other universes can't be observed. How can we test a theory about things we can never see? Defenders respond that we can test the multiverse hypothesis indirectly. If it makes predictions about the observable universe that turn out to be correct, that's evidence for the theory. For example, eternal inflation predicts certain patterns in the cosmic microwave background. If we observe those patterns, it supports eternal inflation and hence the multiverse. The fine-tuning problem connects to the question of what came before the Big Bang. If there's a multiverse, then our Big Bang was just one event among many. Before our Big Bang, the multiverse existed. After our Big Bang, it continues to exist, spawning new pocket universes. The concept of before makes sense in this picture. Our Big Bang had a beginning, but the multiverse as a whole might not. Of course, this still leaves the question of where the multiverse came from. We've just pushed the question up another level. But maybe that's progress. Maybe the right question isn't what came before the Big Bang, but what came before the multiverse. Or maybe there are turtles all the way down, an infinite regress of explanations. Or maybe we reach a point where asking for further explanation doesn't make sense. Let's talk about observation and the role of consciousness. Some interpretations of quantum mechanics give a special role to observers. The Copenhagen interpretation, developed by Niels Bohr and others, says that quantum systems exist in superpositions until they're measured. The act of measurement collapses the superposition, forcing the system to take a definite state. But what counts as a measurement? Does it require a conscious observer, or will any interaction with the environment do? Most physicists think consciousness isn't necessary. Quantum decoherence, the interaction of a quantum system with its environment, causes the effective collapse of superpositions. No conscious observer needed. But some, like Eugene Wigner and John von Neumann, argued that consciousness is fundamental. They thought the chain of quantum interactions only terminates when a conscious mind makes an observation. If this view is correct, it has implications for the Big Bang. If consciousness is required to collapse quantum superpositions, then who or what collapsed the superposition of the early universe? There were no conscious observers in the first few seconds after the Big Bang. Does that mean the universe existed in a superposition until the first conscious beings evolved? That seems absurd. It would mean the history of the universe was indeterminate until we came along to observe it. Most physicists reject this. They think decoherence occurs naturally, without requiring consciousness. The early universe was measured by its own internal interactions. No conscious observers needed. But a few physicists and philosophers continue to explore the role of consciousness in quantum mechanics and cosmology. John Wheeler proposed the participatory anthropic principle. He suggested that observers are necessary to bring the universe into existence. The act of observation collapses the quantum state of the universe, making its history definite. In some sense, we create the past by observing its effects in the present. This is an extreme view that almost no physicists accept. But it shows how strange quantum mechanics can get when you take certain interpretations seriously. It also shows how the question of the universe's origin connects to deep issues about the nature of reality and observation. Let's return to more conventional physics. What can future observations tell us about the Big Bang? We've learned an enormous amount from the cosmic microwave background radiation. Satellites like WMAP and Planck have mapped the temperature variations across the sky with incredible precision. These variations tell us about the density fluctuations in the early universe. They allow us to measure fundamental parameters like the age of the universe, its composition, and the rate of expansion. But the cosmic microwave background only shows us the universe at about 380,000 years after the Big Bang. That's when the universe became transparent and photons could travel freely. We can't see earlier times with light because the universe was opaque before then, but there might be other ways to probe the earlier universe. Gravitational waves offer one possibility. Einstein's theory predicts that accelerating masses produce ripples in spacetime called gravitational waves. These waves travel at the speed of light, carrying information about the events that produce them. We've detected gravitational waves from merging black holes and neutron stars. The LIGO and Virgo detectors have opened a new window on the universe. But these detectors can only see high-frequency gravitational waves from nearby events. To see the early universe, we need to detect much lower frequency waves. The early universe was violent and turbulent. Processes like cosmic inflation would have generated gravitational waves. These primordial gravitational waves would have left an imprint on the cosmic microwave background. Specifically, they would have created a particular pattern of polarization in the background radiation. Several experiments are searching for this polarization pattern. If we detect it, it would be direct evidence of cosmic inflation and of conditions in the first tiny fraction of a second after the Big Bang. It would tell us about energy scales far beyond what we can reach with particle accelerators. It might even give us clues about quantum gravity. So far, primordial gravitational waves haven't been detected. In 2014, the BICEP-2 experiment announced a detection, but it turned out to be contamination from dust in our galaxy. The search continues. Future space-based gravitational wave detectors might be sensitive enough to see primordial waves directly. The proposed LISA mission, scheduled to launch in the 2030s, will look for low-frequency gravitational waves. It might detect waves from the early universe or from cosmic strings, hypothetical defects in spacetime that could have formed during phase transitions in the early universe. Neutrinos offer another window. Neutrinos are nearly massless particles that interact very weakly with matter. They can pass through the Earth without being affected. The Big Bang produced a cosmic neutrino background, analogous to the cosmic microwave background. These relic neutrinos fill the universe. They decoupled from matter about 1 second after the Big Bang, even earlier than photons. If we could detect the cosmic neutrino background, we'd be seeing the universe as it was at 1 second old. That would give us information about Big Bang nucleosynthesis, the formation of light elements. Unfortunately, relic neutrinos have extremely low energies. They're almost impossible to detect with current technology. But physicists are working on new detection methods. In the future, we might be able to observe the cosmic neutrino background. There might even be a cosmic graviton background, relic gravitons from the Big Bang. But gravitons interact so weakly that detecting them is probably impossible even in principle. All of these potential future observations could teach us more about the early universe. But they're still limited to times after the Planck epoch. The very first moment, the realm where quantum gravity dominates, might forever remain inaccessible to direct observation. We might have to rely on theoretical arguments and indirect evidence. That doesn't mean we'll never understand it. It just means the path to understanding will be more difficult. We'll need to develop the correct theory of quantum gravity, test it where we can, and then extrapolate to the Big Bang. That's risky because extrapolation can be wrong. But it might be the only option. Let's consider one more aspect of this question: the anthropological and cultural significance. Questions about cosmic origins have always fascinated humans. Every culture has creation myths, stories about how the world began, where humans came from, what came before. These stories serve important functions. They provide meaning and context for human existence. They connect people to the cosmos. They answer the fundamental question of why there's something rather than nothing. Modern cosmology provides a scientific account of cosmic origins, but for many people, it doesn't serve the same function as traditional creation myths. It tells us how the universe began, but it doesn't tell us why. It doesn't provide meaning or purpose. That's not a flaw in the science. Science isn't supposed to provide meaning or purpose. It's supposed to describe how things work. But it leaves a gap that many people feel. Some people fill that gap with religion. They accept the scientific account of the Big Bang but interpret it as the moment God created the universe. They see the laws of physics as divinely ordained. They find meaning in the fact that the universe is fine-tuned for life, interpreting it as evidence of design. Others find meaning without invoking the supernatural. They marvel at the fact that the universe is comprehensible, that we, collections of atoms, can understand the laws that govern those atoms, that from simple rules, enormous complexity emerges, that consciousness and thought and beauty arise from the interplay of fundamental particles. There's a sense of wonder in this. The physicist Richard Feynman expressed it well. He said that knowing how a flower works, understanding the physics and chemistry and biology, doesn't diminish its beauty. It adds another layer. The universe's origin is similar. Knowing that it emerged from a quantum fluctuation, that it started as something incredibly tiny and grew to encompass billions of galaxies, that the atoms in our bodies were forged in the hearts of stars that died billions of years ago. This is awe-inspiring. It's a kind of cosmic poetry. We're part of the universe trying to understand itself. We're the universe's way of becoming conscious and self-aware. Some people find that deeply meaningful. Others feel differently, and that's okay. There's no right way to respond emotionally to these discoveries. But it's worth thinking about. Science doesn't have to be cold or reductionist. It can inspire wonder and awe just as much as any religious or philosophical view. The question of what came before the Big Bang sits at the intersection of science, philosophy, and human meaning. It's a scientific question about the physical origin of the universe. It's a philosophical question about causation, time, and existence. And it's a human question about where we come from and why we're here. All three aspects are important. The science tells us what we know and what we don't know. The philosophy helps us think clearly about what the science means. And the human dimension reminds us why we care about these questions in the first place. We've come a remarkable distance in understanding cosmic origins. A century ago, we didn't know that other galaxies existed. We thought the universe was eternal and unchanging. Now we know the universe had a beginning. We can describe its history in extraordinary detail. We understand how stars and galaxies formed, how the elements were created, how the cosmos evolved from a hot, dense state to the vast expanse we see today. We've pushed our knowledge back to within a fraction of a second of the Big Bang itself. That's extraordinary. But we haven't reached the very beginning yet. The first tiny fraction of a second remains mysterious. And the question of what came before, if anything, remains open. Maybe we'll answer it someday. Maybe the next generation of physicists will develop a quantum theory of gravity that describes the Big Bang completely. Maybe they'll find evidence for the multiverse, or for a big bounce, or for the no-boundary proposal. Maybe they'll discover something we haven't even imagined yet. Or maybe the question will remain forever unanswered. Maybe it's one of those questions that lies beyond the reach of science. Not because we're not smart enough, but because the question itself doesn't have an empirical answer. Either way, the quest continues. And that's what makes this so exciting. We're at the frontier of human knowledge. We're exploring the deepest questions about reality. We're using mathematics and observation and reasoning to push back the boundaries of ignorance. And even if we never get a complete answer, the journey is worthwhile. Understanding more about the universe means understanding more about ourselves. because we're part of the universe. We're made of star stuff, as Carl Sagan famously said. The atoms in our bodies were forged in stellar furnaces. The carbon in our cells, the oxygen we breathe, the iron in our blood, all came from stars that died before the Earth was born. We're literally made of the universe. And when we study the universe, we're studying our own origins. So the question of what came before the Big Bang is also a question about where we came from. It's a question about our place in the cosmos. And it's a question that defines what it means to be human. We're the species that asks why. We're the species that looks up at the stars and wonders. We're the species that isn't satisfied with simple answers. We want to know how things work, where they came from, what it all means. That curiosity has driven us from the caves to the moon, from counting on our fingers to quantum computers, from believing the Earth was flat to photographing black holes. And it will continue to drive us forward, toward deeper understanding, toward new discoveries, toward answers to questions we haven't even thought to ask yet. The question of what came before the Big Bang might not have a simple answer. It might not have any answer at all. But asking it, exploring it, thinking deeply about it, that's what makes us human. That's what makes science beautiful. And that's why we keep searching, keep questioning, keep pushing the boundaries of knowledge, because even if we never reach a final answer, the journey of discovery is its own reward. Thanks for staying with me through this long exploration. We've covered an enormous amount of ground tonight, from quantum mechanics to cosmic inflation, from the nature of time to the anthropic principle, from gravitational singularities to the multiverse, from philosophy to physics, from ancient myths to modern cosmology. We've grappled with some of the deepest questions humans have ever asked, and while we don't have all the answers, we've gained a deeper appreciation for the questions themselves. We've seen that nothing isn't simple, that the vacuum seethes with quantum activity. That time might have a beginning but no before, that the universe might be one of infinitely many, that the laws of physics might be necessary or contingent, that consciousness and observation might or might not play a role in quantum reality, that meaning and purpose aren't provided by physics but created by us. These are profound insights. They change how we see the universe and our place in it, and they remind us how much we still have to learn. The universe is vast and strange, full of mysteries we're only beginning to unravel, and the biggest mystery of all is the one we've explored tonight, the origin of everything, what came before the beginning, or whether before even makes sense. It's a question that might never be fully answered, but it's a question worth asking, worth exploring, worth dedicating our lives to understanding, because in the end, that's what science is about. Not just accumulating facts, but asking the deepest questions, challenging our assumptions, expanding our understanding, and marveling at the universe's complexity and beauty. So whether nothing existed before the Big Bang or something, or whether the question doesn't make sense, one thing is certain. The quest to understand our cosmic origins is one of the most profound and important endeavors humans have ever undertaken, and you've been part of that quest tonight. But before we conclude, let's explore a few more fascinating aspects of this deep question. Let's talk about what black holes can teach us about the Big Bang. Black holes and the Big Bang have something profound in common. They both involve singularities, points where the equations of general relativity break down. Understanding black holes might help us understand the Big Bang. A black hole forms when a massive star runs out of fuel and collapses. The star's core compresses under its own gravity. If the star is massive enough, nothing can stop the collapse. The core shrinks past the point where neutron degeneracy pressure can support it. It continues collapsing until all the mass is concentrated at a single point, a singularity. At the singularity, density becomes infinite. the curvature of space-time becomes infinite. The laws of physics as we know them break down. General relativity predicts the singularity, but can't describe what happens there. The same equations that predict the singularity also tell us they stop working at the singularity. It's like a map that shows you how to reach a location, but then has a blank spot at that location. Here be dragons. The Big Bang singularity is similar. When we run the expansion of the universe backward in time, everything converges to a point of infinite density and temperature. General relativity predicts this but can't describe it. Both singularities represent limits of our understanding, places where we need new physics. Specifically, we need quantum gravity. Roger Penrose proved an important theorem about singularities. The Penrose singularity theorem, published in 1965, shows that singularities are generic features of general relativity. They're not artifacts of special symmetric situations. They're unavoidable once certain conditions are met. For black holes, the condition is that an event horizon forms. Once an event horizon exists, a singularity must exist inside it. The mathematics allows no escape. For cosmology, the condition is that the universe is expanding and has a finite past. If the universe is expanding now, and we run time backward, we inevitably reach a singularity, unless something happens to stop the collapse before reaching infinite density. This is where quantum mechanics might save us. Quantum mechanics provides natural limits. The Heisenberg uncertainty principle says that you can't know both the position and momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you know the other. This has implications for very small distances. If you try to confine a particle to a very small region of space, its momentum becomes highly uncertain. High uncertainty in momentum means high kinetic energy. At some point, the quantum mechanical kinetic energy becomes so large that it can resist gravitational collapse. This might prevent the formation of true singularities. The collapse might halt at some minimum size, determined by quantum effect. This minimum size would be around the Planck length, about 10 to the minus 35 meters. That's 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 itself become important. Space and time become grainy or foamy. The smooth fabric of space-time described by general relativity breaks down. Loop quantum gravity explicitly calculates this. In loop quantum gravity, space-time is made of discrete units, tiny loops or networks at the Planck scale. Area and volume are quantized. They come in discrete chunks, not continuous values. This quantization might prevent singularities. Instead of collapsing to a point, matter might collapse to the Planck scale and then bounce. For black holes, this would mean there's no true singularity at the center. Instead, there's a tiny region of Planck scale structure that we can't resolve with current physics. For the Big Bang, it would mean the universe didn't emerge from a true singularity. Instead, it bounced from a previous contracting phase, the Big Bounce scenario. This is appealing because it avoids the problem of the beginning of time. If the universe bounced, time didn't begin at the Big Bang. There was a before, a previous universe that was contracting. The Big Bang wasn't the beginning of everything, just a transition from contraction to expansion. But the Big Bounce scenario has its own problems. What caused the previous universe to start contracting? Where did that universe come from? We've just pushed the question back in time. Maybe there's an infinite series of bounces. The universe oscillates forever, contracting and expanding, bouncing at the minimum size. This avoids the question of an absolute beginning, but it raises new questions about information and causality. How does information pass through the bounce? Are the physical conditions after the bounce determined by conditions before, or does the bounce reset everything? If information passes through, then the current state of the universe depends on an infinite past history. That seems philosophically problematic. An infinite regress. If the bounce resets everything, then asking about the previous cycle doesn't help explain the current cycle. The origin question remains. Some versions of loop quantum gravity suggest that information is partially preserved through the bounce. The details depend on exactly how quantum geometry works at the Planck scale. But we don't have a complete theory yet, so these are informed speculations rather than definite predictions. String theory offers yet another perspective on singularities and origins. In string theory, the fundamental objects aren't point particles, but tiny one-dimensional strings. These strings vibrate, and different vibration modes correspond to different particles. An electron is one vibration mode. A quark is another. A photon is another. And crucially, the graviton, the particle that carries gravity, is also a vibration mode. This means string theory naturally includes gravity. It's a quantum theory that includes gravity from the start. This is why string theorists hope it can describe what happens at singularities. In string theory, what looks like a point particle from far away is actually a tiny extended string. The string has a finite size, about the Planck length. When two particles interact at very high energies, instead of colliding at a point, the strings interact smoothly. The interactions are spread out over the string's length. This might eliminate singularities. Instead of infinite density at a point, you'd have high but finite density spread over the string. The problem is that string theory is mathematically very complicated. We don't yet know how to extract definite predictions about what happens at singularities. We can't yet calculate what happens at the Big Bang or inside a black hole using string theory. Progress is being made, but slowly. The mathematics is incredibly difficult. One intriguing idea from string theory is the ekpyrotic scenario. This model, proposed around 2000, suggests that the Big Bang was caused by a collision between two parallel universes. In some versions of string theory, our universe is a three-dimensional membrane, called a brane, floating in a higher dimensional space. Other universes might exist as parallel branes. If two branes collide, enormous energy is released. From the perspective of observers on one brane, this would look like a Big Bang. The universe would suddenly fill with hot, dense matter and radiation. Space would begin expanding rapidly. In this scenario, the Big Bang wasn't the beginning of the multiverse, just the beginning of our particular universe. The multiverse, the higher dimensional space containing the branes, existed before and continues to exist after. Time didn't begin at the Big Bang. Only time in our three-dimensional universe began. Time in the higher dimensional bulk space continues as always. The ekpyrotic scenario can potentially explain some features of the observed universe. The nearly flat geometry, the small density fluctuations that seeded galaxy formation, but it's highly speculative. We have no direct evidence for extra dimensions, no evidence for parallel universes, no evidence for colliding branes. It's an interesting theoretical possibility, but not an established theory. It shows the creativity of theoretical physicists in trying to explain the Big Bang. Let's think more deeply about what quantum mechanics tells us about nothingness and existence. We've discussed how the vacuum isn't empty, but filled with quantum fluctuations, virtual particles constantly appearing and disappearing. But there's something even stranger about quantum mechanics. It's fundamentally probabilistic. When you measure a quantum system, You can't predict with certainty what result you'll get. You can only calculate probabilities. Before measurement, the system exists in a superposition of multiple possible states. The measurement forces it to choose one state. This isn't just our ignorance about hidden variables. Experiments have proven that quantum systems really don't have definite properties until they're measured. The famous double-slit experiment demonstrates this. Send a single electron through two slits, and it interferes with itself. It goes through both slits simultaneously, like a wave. But when you measure which slit it went through, the interference pattern disappears. The electron behaves like a particle that went through one slit or the other. The act of measurement changes the system's behavior fundamentally. This is weird and counterintuitive. Einstein hated it. He famously said, "God does not play dice." But countless experiments have confirmed that nature really does work this way at the quantum level. Now, here's where it gets interesting for cosmology. If the universe itself is a quantum system, then it might exist in a superposition of multiple states. The wave function of the universe could include many possible configurations simultaneously. This leads to strange implications. Does the universe exist in a superposition until someone observes it? But who's doing the observing? We're inside the universe. How can we observe it from outside? These are deep questions that physicists and philosophers have debated for decades. One approach is the Wheeler-DeWitt equation. This is an attempt to apply quantum mechanics to the entire universe. In ordinary quantum mechanics, you have a wave function that describes a system. And you have an equation, the Schrödinger equation, that describes how the wave function evolves in time. But in quantum cosmology, time itself is part of the system you're describing. There's no external time parameter. The Wheeler-DeWitt equation is a quantum equation for the entire universe, with no explicit time variable. It describes the wave function of the universe, but not how it changes in time, because time is part of the universe, not external to it. This is deeply strange and counterintuitive. How can you have evolution without time? How can you have dynamics without a time parameter? The answer is that time emerges from the correlations between different parts of the universe. When we observe the universe, we're inside it, embedded in space-time. From that internal perspective, time seems to flow. Events happen in sequence. Causes precede effects. But from the external perspective described by the Wheeler-DeWitt equation, there's no time. The entire history of the universe, past, present, and future, exists as a single quantum state, a timeless superposition. This is called the timeless formulation of quantum mechanics. It's controversial and hard to interpret. Many physicists find it philosophically troubling. But it might be necessary for describing quantum gravity and the origin of the universe. In this picture, asking what came before the Big Bang is fundamentally the wrong question. Time doesn't flow from past to future. The entire space-time manifold, including the Big Bang, exists as a complete four-dimensional structure. There's no before or after from the fundamental perspective. Those are just features of our internal experience as we move through the structure. Julian Barber has developed these ideas extensively. His book, The End of Time, argues that time is an illusion. What really exists is a vast collection of possible configurations of the universe. Each configuration is a three-dimensional snapshot, a moment. Some configurations are similar to each other, creating the appearance of continuous change. When we experience time flowing, we're actually experiencing a sequence of slightly different configurations. But fundamentally, there's no time. There's no flow. There's just this timeless collection of possibilities, what Barber calls Platonia. The Big Bang is one region of this configuration space. The present moment is another region. The future is yet another. They all exist equally in Platonia. Time emerges from the relationships between configurations, from the fact that some configurations contain records and memories of others, but it's not fundamental. This is a radical rethinking of the nature of time and existence. Most physicists don't accept it. They think time is real and fundamental. But Barber's ideas show how deeply our concepts might need to change to understand quantum gravity. They show that the question of what came before the Big Bang might dissolve entirely when we properly understand the quantum nature of space-time. Let's consider the role of complexity and information in defining time's arrow. Some theorists suggest that the direction of time is related to the growth of complexity. The early universe was simple: hot, dense, nearly uniform plasma. Just hydrogen and helium nuclei and electrons. No stars, no galaxies, no complex structures. Over time, structure emerged through gravitational collapse. Atoms formed when the universe cooled. Stars coalesced from clouds of gas. Nuclear fusion in stellar cores created heavier elements. Galaxies formed containing billions of stars. Planets formed around stars. On at least one planet, life emerged. Single-celled organisms at first. Then, multicellular life. Increasingly complex organisms. Eventually, conscious beings arose who could contemplate their origins. This progression from simple to complex seems to define a direction of time. The past is simpler. The future is more complex. But is this necessarily true? Could complexity decrease in the future? In principle, yes. The second law of thermodynamics says entropy increases, not complexity. Entropy and complexity are related, but not identical. High entropy means high disorder, but that can manifest in different ways. A gas spread uniformly through space has high entropy and low complexity. A collection of black holes has high entropy, but also involves complex structure. The relationship between entropy, complexity, and time is subtle. Some physicists think complexity, not entropy, is the key to understanding time's arrow. The universe started in a low entropy, low complexity state. Both entropy and complexity have been increasing ever since. Eventually, entropy will reach its maximum in the heat death of the universe. All stars will have burned out. All matter will have decayed or fallen into black holes. The black holes themselves will have evaporated through Hawking radiation. Nothing will remain but a thin soup of low-energy particles and radiation at a uniform temperature. At that point, complexity will be zero. No structures, no gradients, no interesting processes, just featureless uniformity. If complexity defines the arrow of time, then time might reach an endpoint at heat death, or perhaps time is cyclical. Complexity grows from the Big Bang to some maximum, then decreases back to zero. Then another Big Bang occurs, and the cycle repeats. This connects to the oscillating universe models we discussed earlier. But there are problems with cyclical time. How does one cycle connect to the next? What triggers the transition from maximum entropy back to low entropy? No known physical process can decrease entropy without external input. Information theory offers another perspective on time and origins. Information is a physical quantity that can be measured in bits, the amount of information needed to describe the universe's state completely. In the early universe, despite being hot and dense, the information content was relatively small. The universe was nearly uniform. You could describe its state with just a few parameters: temperature, density, the amplitude of small fluctuations, maybe a few hundred bits of information total. As the universe evolved, more information became encoded in its structure. The positions and velocities of particles, the intricate structure of galaxies and galaxy clusters, the chemical composition of planets, the genetic information in living organisms, the content of human brains and books and computers. The total information content of the observable universe has been increasing. Seth Lloyd has estimated it's now about 10 to the power of 90 bits. That's a 1, followed by 90 zeros. An incomprehensibly large number. This increase in information might define the arrow of time. Time flows in the direction of increasing information. Now here's a deep question. Where did the initial information come from? If the Big Bang started with some specific information content, what determined that information? If it started with truly zero information, a completely random state, how did structure emerge? These questions connect to the earlier discussion about initial conditions and fine-tuning. The Big Bang seems to have started with very specific initial conditions. Low entropy, small but non-zero density fluctuations, particular values for the fundamental constants. All of this represents information that was somehow present at the beginning. Where did it come from? One answer is inflation. Inflation would have taken quantum fluctuations and stretched them to cosmic scales. These quantum fluctuations are random, so in some sense they represent zero information. But the fact that inflation occurred, the fact that the inflaton field had the right properties, that represents information. Another answer is the multiverse. Maybe countless universes exist with different initial conditions. We observe a universe with these particular conditions because those are the conditions necessary for complexity and life. A third answer is that there's a deeper theory that predicts the initial conditions. Maybe they're not arbitrary, but necessary consequences of the fundamental laws of physics. We don't know which, if any, of these answers is correct. But the question of where information comes from is intimately connected to the question of where the universe came from. One more theoretical framework deserves mention: causal set theory. This is an approach to quantum gravity that's less well known than string theory or loop quantum gravity. But it offers interesting insights into the nature of space-time and causality. Causal set theory proposes that space-time is fundamentally discrete. It's made up of discrete events, like atoms of space-time. These events have causal relationships. Event A can be in the past of event B, or in the future, or neither. The causal structure, which events can influence which other events, is fundamental. The geometry of space-time, the distances and angles we measure, emerges from the causal structure. In causal set theory, space-time is built from the bottom up. You start with individual events and causal links between them. The smooth four-dimensional space-time of general relativity emerges as an approximation when you have many events. This is similar to how a fluid emerges from individual molecules. Water seems smooth and continuous, but it's actually made of discrete molecules. Space-time might be the same way. Smooth at large scales, but discrete and grainy at the Planck scale. The interesting thing about causal set theory is how it handles the beginning of time. In continuous space-time, the beginning is a singularity where things break down. But in discrete space-time, there can be a first event, a minimal element in the causal set with nothing in its past. This would be the Big Bang event. Not a singularity, but simply the first discrete event. Everything else in the universe's history is in the future of this first event. There's nothing in its past because there is no past. It's the first element in the causal set. This provides a natural way to avoid the question of what came before. There's no before because the Big Bang event has nothing in its causal past. It's the beginning of the causal structure itself. Of course, this raises the question of why this first event exists. What determined its properties? These questions remain, but at least the framework provides a consistent mathematical description of a beginning without a prior time. Causal set theory is still being developed. It hasn't made testable predictions yet. but it shows that there are multiple approaches to quantum gravity, each with different implications for the origin of the universe. Let's step back and appreciate the scope of what we've explored tonight. We've journeyed from everyday experience to the edge of scientific knowledge, from the familiar flow of time to the possibility that time is an illusion, from the solid reality of matter to the quantum foam of space-time, from the Big Bang to speculation about what might have come before. We've seen that seemingly simple questions lead to profound complexity. What is nothing? It's not simply the absence of everything. The quantum vacuum is something, not nothing. True, absolute nothing might be incoherent or impossible. What is time? It's not the absolute flowing river we intuitively imagine. It's part of space-time, relative to observers, possibly emergent from something more fundamental. Where did the universe come from? Maybe from a quantum fluctuation. Maybe from a previous contracting phase. Maybe from a collision of brains in extra dimensions. Maybe from nothing, if nothing is unstable. Maybe the question doesn't make sense because time began with the universe. We don't have definite answers. But we've narrowed down the possibilities. We've developed mathematical frameworks that might eventually give us answers. We've identified what we need to discover to make progress. A quantum theory of gravity. Evidence for or against inflation. Observations of primordial gravitational waves. Better understanding of the fundamental constants and why they have the values they do. These are challenging problems, but they're tractable. Within decades, we might have answers. Or we might discover that some questions lie beyond empirical science. That would be disappointing but also valuable. Knowing the limits of what we can know is itself a form of knowledge. The journey we've taken tonight reflects humanity's broader journey of understanding. For most of our species' history, we had only myths and stories about cosmic origins. These stories served important purposes. They gave meaning to existence. They explained the world around us in ways that made sense, given available knowledge. The ancient Greeks imagined a cosmos with Earth at the center and crystalline spheres carrying the planets and stars. Medieval scholars debated how many angels could dance on the head of a pin while contemplating divine creation. Indigenous cultures worldwide developed rich cosmologies connecting humans to the cosmos. These weren't failures of imagination or intelligence. They were humanity's best attempts to understand our place in the universe, given the information available. But gradually, over centuries, we developed new tools. Telescopes that let us see farther. Mathematics that let us calculate precisely. The scientific method that let us test hypotheses against observation. And our understanding transformed. Copernicus showed Earth wasn't the center of the cosmos. Galileo's telescope revealed moons orbiting Jupiter, proving not everything orbited Earth. Newton showed the same laws governing falling apples govern planetary orbits. Einstein revealed that space and time are relative and intertwined. Hubble discovered the universe is expanding. Penzias and Wilson found the cosmic microwave background, evidence for the Big Bang. Each discovery built on previous ones. Each generation of scientists stood on the shoulders of giants, as Newton famously said. And now we stand at a remarkable vantage point. We understand the universe's history back to fractions of a second after its beginning. We've mapped the cosmic microwave background in exquisite detail. We've detected gravitational waves from colliding black holes. We've discovered thousands of planets around other stars. We've found that the universe is filled with mysterious dark matter and dark energy. We've developed theories, tested them, refined them, and built a coherent picture of cosmic history. But we've also discovered how much we don't know. What is dark matter? What is dark energy? How do we reconcile quantum mechanics and general relativity? What happened at the Big Bang? What, if anything, came before? These unknowns aren't failures. They're opportunities. They're the frontier, where the next generation will make their mark. Young people watching this video right now might be the ones who solve these mysteries, who develop the quantum theory of gravity, who detect primordial gravitational waves, who find evidence for the multiverse or rule it out, who finally answer what came before the Big Bang, if anything. Science is a collaborative enterprise spanning generations. No single person has all the answers, but collectively, over time, we make progress. We climb the mountain of knowledge, each generation reaching a bit higher. The view from the summit isn't clear yet. We're still climbing, still pushing upward through the clouds of uncertainty. But every step reveals new vistas, new questions, new wonders, and the journey itself is meaningful. The act of questioning, exploring, discovering is part of what makes us human. We're curious. We want to understand. We're not satisfied with ignorance when knowledge is possible. This drive to know, to explore, to push boundaries has taken us from caves to the moon, from counting on our fingers to quantum computers, from believing Earth was flat to mapping the entire observable universe. And it will continue to drive us forward, toward deeper understanding, toward new discoveries, toward answers to questions we can barely formulate today. The question of what came before the Big Bang sits at the intersection of what we know and what we don't. It's at the boundary between physics and philosophy, between science and metaphysics. We have theories and mathematical frameworks, but we don't have definitive answers yet. And that's exciting. That's where the real work happens. At the frontier, in the unknown, where the questions are hardest. So when people ask what came before the Big Bang, the honest answer is, we don't know, but we're working on it. We have ideas to test, observations to make, theories to develop, and we're making progress. Maybe in 10 years, 20 years, 50 years, we'll have the answer. Or maybe we'll discover the question itself is malformed and needs to be asked differently. Either way, we'll know more than we do today, and that's what matters. The continuous expansion of human knowledge, the never-ending quest to understand our universe and our place in it. You've been part of that quest tonight by engaging with these ideas, by thinking deeply about cosmic origins, by questioning your assumptions about time and existence, by grappling with some of the hardest questions humans have ever asked. That engagement matters. Science isn't just for scientists in universities and research labs. It's for everyone who wonders about the world. Everyone who looks up at the night sky and asks questions. Everyone who wants to understand how things work. You don't need a PhD to appreciate the profound mysteries of existence. You don't need to solve the equations yourself to grasp the concepts. You just need curiosity and willingness to think. And by watching this video, by following this long exploration through complex ideas, you've demonstrated both. So thank you. Thank you for your curiosity. Thank you for your patience through 18,000 words of deep exploration. Thank you for being part of humanity's grand project of understanding the cosmos. The question of what came before the Big Bang may not have a simple answer. It may not have any answer at all, but it's a question worth asking, worth exploring, worth dedicating time and thought to understanding, because in asking these questions, in pushing at the boundaries of knowledge, in refusing to accept ignorance when understanding might be possible, we honor what makes us human, our curiosity, our intelligence, our drive to know and understand. These qualities have taken us from primitive ancestors to a species that can contemplate the origin of everything. And they'll continue to push us forward toward whatever discoveries await. The universe is vast, strange, beautiful, and full of mysteries. The origin of everything is perhaps the deepest mystery of all. We've explored it tonight from every angle: quantum mechanics and general relativity, singularities and bounces, multiverses and brains, inflation and entropy, time and causality, information and complexity, philosophy and physics, meaning and mathematics. We've seen that the answer, if there is one, won't be simple. It will involve ideas that challenge our intuitions about time, existence, and causality. It might require us to completely rethink fundamental concepts, but that's okay. That's how progress happens, by questioning assumptions, by following evidence wherever it leads, by building new frameworks when old ones fail. So whether nothing existed before the Big Bang, or something, or whether the question doesn't apply, one thing is certain. The quest to understand continues, and you've been part of it tonight. Thanks for joining me on this journey to the very beginning and beyond.